Greetings, AP Chem minions. By request, we have an electrolytic cell problem. First and foremost, how can we tell is it an electrolytic cell? Well, there's an external power source. Right now, we can tell that by these fabulously drawn bubbles that there are gases being formed at each electrode. But otherwise, we do not know which one is the anode and which one is the cathode. But we'll get to that later. All we know is that poor innocent water molecules are being electrocuted. So let's look at the first two questions, A and B. We want to write the balanced equation for each half reaction. Okay, what I've pasted down here comes from that table of standard reduction potential values. This would have to be given to you as part of the question stem. So let me label this. Okay. Now, the next part. Something you just have to have memorized is which is the equation for reduction of water and which is the equation we use for the oxidation of water. I use that water oxidizes into oxygen. So this is our oxidation half, and this is our reduction half. I'm going to scroll down a bit so that I can write out the answers. So question A wants our oxidation half reaction. So we have 2 water going to oxygen gas plus 4 hydrogen ions plus 4 electrons. Now for the reduction half, okay, it's in the correct order. But you probably will notice that our electrons are not going to cancel out. So the balanced half for this equation actually needs to make this a 4, that a 4, this a 2, and that a 4, because we are multiplying the entire equation by 2 in order to get what is asked for in question C, our balanced net equation. So I'm going to sum this. So we've got 2 water plus 4 water giving us 6 water. And 1 oxygen gas molecule plus 2 hydrogen gas molecules plus 4 hydrogen ions. And I'm running out of space, so I'm not going to put the states on these. Now, you should recall from previous redox that whenever you have hydrogen and hydroxide ions together, they combine to make water. So this is now 4 water molecules. And we've got water on both sides, so somebody's going to get canceled out. Since there's more water on this side, this water is going to go away completely, and this one is going to become 2. So the final answer for this one is 2 water molecules becoming an oxygen molecule and 2 hydrogen molecules. All right, scrolling back up so we can see the question. Question D says to label the anode and the cathode on the diagram above and write the half reaction that takes place at each electrode. Okay. Since there's no other indication of which is which, we can label this however we want to. Okay? I can arbitrarily say that this is the anode and that this one's the cathode. Or you could put it the other way. The important point is that you put the correct equation. And what you're supposed to remember is that reduction happens at the cathode and oxidation happens at the anode. Let me fix that scrolling. Okay, so we've got our label. We're going to say this one's the anode where the oxidation happens, this one's the cathode where the reduction happens. So rather than write out the equation, just know that your answer from A should be listed over here and your answer from B should be listed over here. All right. Question E, in which direction do the electrons flow? Electrons always flow away from the anode. So since we said this one's the anode, they're going to flow down this wire this way and towards the cathode. All right, and then question F. Okay, this one's a little bit more involved. You have 2.5 amps of current flowing through the circuit for 13.6 minutes. We're at 25 degrees Celsius and 1 atmosphere. What volume of hydrogen gas is produced? So 25 degrees Celsius and 1 atmosphere is standard conditions for an electrochemical cell. However, it is not standard conditions for the production of a gas. So we're going to have to do two different things. I'm going to scroll down just a little bit more to make some room up to where I can see the problem. All right, so this is, no, that's question F, sorry. All right, one of the things you need to remember is that 2.50 amperes is the same thing as 2.50 coulombs per second. And we know we have 13.6 minutes. We need to convert that to seconds. So every minute has 60 seconds. So I'm multiplying my 13.6 times 60, and I get 816 seconds. So now for your setup. For the first part, we're going to do 816 seconds times 2.50 coulombs per second. So now our seconds have canceled. We have coulombs of charge. And then the next key piece of the puzzle is using Faraday's constant, which is something given to you on your equation sheet. And it says that there is 96,500 coulombs of charge per 1 mole of electrons. Well, now we have moles of electrons, but we're trying to get to hydrogen gas. So let's look at it. Refer back to our equation. Now remember, we had doubled this one in order to make it a balanced half, but in our original equation that there are 2 moles of electrons per 1 mole of H2. So I'm going to do this, a mole ratio. And now we need this answer, which is going to be our moles of H2. So plugging that into your calculator, you should do 816 times 2.5, and then use parentheses judiciously, divide that by 96,500 times 2. And we get a small number, 0.0106. Scroll down a little bit more. All right, but we're not finished. We are not at STP, at least not for gases. We're at 25 degrees Celsius, which is 298 Kelvin, but we are at 1 atmosphere of pressure. We are going to have to pull out the ideal gas law. Perv nert. All right, so pressure was given to us, the 1 atmosphere. We are looking for the volume. Moles of gas was what we just calculated. The R value is something that you have to look up. Again, that's on your equation sheet. But when pressure is measured in atmospheres, it's 0.0821. And then our temperature in Kelvin, 298. So plugging that in, 0.0106 times 0.0821 times 298. And rounding our answer to 3 significant figures, we get 0.259 liters, which is 259 milliliters. And that completes your problem. Happy watching!